Okay, everyone. So we're moving on to section 3.4. This is the second derivative test, and it also has to do with something called concavity. So concavity, what does that mean? So you can think of concavity as sort of bending, which way a function is bending, right? So the official definition, and again, I'm using my pen here, see if this works. Okay. A graph is concave upward on an interval when the first derivative is increasing. So that seems a little confusing. What does it mean for the derivative to be increasing? It means that the slope is getting bigger. So as you're going left to right, the slope might be negative, it might be positive, but it's getting bigger and bigger and bigger. In other words, it's bending upward. So when you see something bending upward, that means it's concave up. Okay? On the other hand, if the derivative is decreasing, say it might start out very big, but then it gets smaller and smaller and smaller, eventually more negative, that means it's concave down. Okay? Right. So this is the definition, but the easiest way to determine, given a function, whether it's concave up or concave down is to use the second derivative. If the second derivative is positive, it's going to be concave up on that interval. And if the second derivative is negative, it's going to be concave down on the interval. And now you might ask, well, what happens if the second derivative is 0? Well, if the second derivative is 0 at a specific point, you really can't say anything about that point. But let's say the second derivative is 0 everywhere. So let's think about that. If the second derivative is 0, right, for all x, it turns out, and this may or may not be clear at this point, but it turns out that there's only one type of function that has this property, and that's a linear function. So I'll just call it mx plus b. Right? In other words, it's a straight line. So the graph will just be a straight line, right? So what's true about a straight line? Right, so here the slope is positive. Again, so that's the first derivative. We're worried about the second derivative, right? The second derivative is 0. So what's true about a line? It's not bending, right? It's not bending at all. So it doesn't have concavity. It's not concave up, it's not concave down. It's not bending at all, right? If it was bending even just a little bit, like this, we could say it's concave up. If it's bending a little bit like this, it's concave down, right? So I want to make it clear that, concavity has nothing to do with increasing, decreasing. Here I just picked a line with a positive slope. We can pick a line with a negative slope. But again, it's not bending. It's not bending up or down. So it doesn't have concavity, right? You could say the concavity is 0 or just say that it's not concave up or down. Okay, so straight lines don't have concavity, right? They might be increasing, they might be decreasing, but they don't have concavity. Only curves have concavity, right? Okay. Right, so next definition is you have a continuous function on an open interval containing C. If a graph has a tangent line at that point, at CF of C, we say the point is an inflection point if the concavity changes, right? So here, this is concave up everywhere. This is concave down everywhere. The concavity is not changing, right? Which means there's no inflection points here, right? So let me draw a graph of something that has an inflection point, right? So let's say we're concave down. We have a graph that's concave down like this, and then suddenly it changes and it's concave up like this, right? Or let's say it keeps going and then at some point it changes back to concave down and then concave up again, and so on, right? So what we can say is that right around here, right around at that point there, to the left of that point, it's concave down, and to the right of that point, it's concave up. So let me try this. Hang on. So pretend this is the x-axis, right? This is my C right here. Now, be careful. C is not for critical number here. we don't have it, well, I don't have another letter, so the book uses C again, but be careful. C does not stand for critical number here. And we know it's not a critical number because the tangent line is not 0. That doesn't have slope 0, okay? And it does exist, it's just some negative number, so not a critical number. Right, what we're concerned with, though, is that the second derivative, right, is going to be negative because it's concave down, and then it changes to positive. So it's concave up, right? So remember, this is the second derivative now, not the first derivative. So the second derivative changes from negative to positive. When that happens, we say that we have an inflection point at C, and then, of course, being a point here, and has a y-coordinate f of C. Right, so that would be a point of inflection, or I just call them inflection points. So this is an inflection point on the graph, right about there, right. And you can go the other way. In other words, you can have a point where the sign changes. So I think that happens right about here on the graph. Oh, I can't go vertical here. So here's another C, say C2, C1. At C2, notice the sign of the derivative changes from positive to negative. Why is it negative here? Because it's concave down, right? So this point here becomes another inflection point. Right? This is also an inflection point. And right around here, oops, say C3, this is also an inflection point because the concavity changes from down to up, or the second derivative changes from negative to positive. So 3 inflection points, right? So if the concavity changes, that's what makes it an inflection point, right? So how can you find your inflection points? Take the second derivative, set it equal to 0, and solve for x, right? If you get those, they are possible inflection points, right? Possible inflection points, not necessarily inflection points. And maybe I should do a quick example to show you what I mean. So here's an example. I'll call this example 1. And very simple function, f of x equals x to the 4th. Okay, so find the inflection points. We want the inflection points. Right. So according to this, if you have an inflection point, then the second derivative is 0 or fails to exist. But that doesn't mean the opposite. In other words, if the second derivative is 0 or does not exist, that doesn't mean it's an inflection point. So let's see what happens, right? If we take the first derivative, oops, we get 4x cubed. I hope that's clear by now. But we need the second derivative. The second derivative is 12x squared. So where does that equal 0? Well, divide by 12, take the square root, x equals 0. All right. So does that mean it's an inflection point at x equals 0? Not necessarily. This is where you have to be careful. All right. Let's draw the number line here. 0 is our possible inflection point. Remember, we're not looking for maximums or minimums, so we don't want the first derivative. We want this, the second derivative. Let me try that again. Second derivative. So what happens when you plug in a negative number, less than 0, into the second derivative? Well, negative 1 squared is positive 1, times 12 is positive 12. So the second derivative is positive here. And what happens when you plug in a positive number, like 1? It's still 12. It's still positive. So notice the sign of the second derivative does not change at 0. And if remember what an inflection point is. It's where the concavity changes. It doesn't change here. It's concave up and still concave up, right? In other words, the graph might look something like this. It's concave up and it's still concave up. Right? So in fact, you do have a minimum here. You can check that with the first derivative test. If you look at the sign of the first derivative, it changes from negative to positive, and so you get a relative minimum at 0. but that wasn't the question. The question is, what are the inflection points? And then the answer is, there are none. There are no inflection points. So, none for inflection points. Yep. So again, the easiest way to determine whether one of these possible points is an inflection point or not is to do the sign chart, but for the second derivative now, not for the first derivative. And if the sign changes, it's an inflection point. If the sign does not change, it's not an inflection point. Okay, so just want to be clear on that. Okay, so that's it for concavity, right? I hope this is clear. What's concave up, what's concave down, right? Has nothing to do with increasing or decreasing, right? Because the function could be decreasing or increasing and yet concave up. The function could be increasing or decreasing and yet concave down. Okay? All right, so that brings us to the next theorem, the next property, called the second derivative test. And in a way, this is superfluous. This is not really necessary because it does the exact same thing as the first derivative test. It determines whether a critical number, remember critical numbers, whether the critical number is a maximum or a minimum. And so the second derivative test essentially does the exact same thing here. So I'm going to do another example. Actually, but before I do the example, let's just say what the second derivative test is, right? So you have a function that's twice differentiable. It means you need the second derivative, whose first derivative is 0, right? So C is a critical number now. C is going to be a critical number, but you have to be careful because it's not going to be a critical number where the derivative fails to exist, right? It's a critical number because the derivative equals 0. So that means it has to have a tangent line. Okay? So if this is true and you take the second derivative, if you plug in the critical number into the second derivative, if you get a positive, remember what that means. Positive second derivative means it's concave up. Concave up, oh, I need a darker color here. Let's use this. Concave up means that it's concave up. It looks like this. So if this is my C right here in the middle, that tells me I have a relative minimum, right? On the other hand, if the second derivative is, oops, I lost my marker here. Yep, if the second derivative is negative, that means it's concave down, right? And at your critical number, if this is my critical number up here, that tells me I have a maximum, okay? However, that's only two possibilities, that the second derivative is either positive, meaning you have a minimum. If the second derivative is negative, you have a maximum. What if the second derivative is 0? Well, you have to be careful. You might conclude that, well, then it's neither. It's one of those points where it looks like this, right, where it's neither a minimum nor a maximum. Unfortunately, you cannot conclude that here. That's a possibility, but if the second derivative equals 0, you really have no idea. The test just doesn't work. Because if the second derivative is 0, you could have a point where, like an inflection point here, where you don't have a minimum or a maximum. But the other possibility is that you have a minimum. The other possibility you have a maximum. When the second derivative is equal to 0 at your critical number, you simply can't tell whether it's a minimum or maximum, or neither. The only way to know is to go back and use the first derivative tests to do that. Okay, so I think with that we can do an example. So let's do example 2 here. I know I'm making this video maybe a little longer, but let's see if this works. So use the second derivative test to determine the relative extrema. So again, find the relative extrema. In fact, I'll just say maximum, minimum of the function. And again, I'll start with an easy one. Let's just do x cubed plus 6x squared minus 96x plus 12. Right? So how do you find the relative extrema, the maximum, minimum? As always, critical numbers. So we need the first derivative, which is 3x squared plus 12x minus 96. So the only critical numbers here were the derivative equals 0. So if you factor out the 3, you get x squared plus, plus 4x minus 96 divided by 3, 32. Sorry, my arithmetic is bad. I needed a calculator for that. Hang on, 32. Yep, equals 0. Okay, so that's the first derivative, and I think we can do a little better than that. We can factor this. This will be x plus 8 times x minus 4. Right? 8 minus 4 is 4, and 8 times negative 4 is negative 32. So we get two critical numbers, negative 8 and 4. Remember, 3 is not a critical number. That's just the coefficient. Right? Now, at this stage, you did this already, right? Using the first derivative test, you can make your little sign chart. You can do negative 8 and 4, positive 4, and determine the signs in between these and to the left and to the right. So we did that already. So that's, that's not hard. I'll let you do that if you want. But we're going to do it a different way. We're going to use the second derivative test at this point. So obviously, to use the second derivative test, we need the second derivative. And to take the second derivative, I would not use this because you're going to use the product rule here. I would go back to this version. Taking the derivative of this gives us 3 times 2x, so 6x plus 12. Okay. So again, the second derivative test turns out to be just as easy as the first derivative test, especially when the second derivative is this simple. And in fact, you can, if you want, you can factor out a 6 and just make it 6 times x plus 2. Remember, we're not finding critical numbers, so we're not finding inflection points, so we don't need to know where this equals 0. But maybe I'll just mention that at x equals negative 2, you have a possible inflection point. But that wasn't the question, right? The question is to find the relative maximum and minimum. And we have two possibilities here, negative 8 and positive 4 for our maximum minimums. So the nice thing about the second derivative test is the following. You don't have to plug in numbers left and right. You just plug in numbers into the second derivative. The negative 8, that's the c here. And what do we get? We get 6 times negative 8 plus 12. Negative 48 plus 12, I guess, is negative 36 or something. Doesn't matter. We know it's negative. So the second derivative test says, remember, if the second derivative is negative, be careful. You don't have a minimum, you have a maximum. So f has a relative maximum at negative 8. And you can plug into the original function to get the y value. Yep, I'll let you do that. Right? So we didn't have to look left and right. We just plugged the negative 8 into the second derivative. And because it's negative, we get a maximum. Remember, why do we get a maximum when it's negative? Remember what a second derivative is. It's concavity. And the second derivative is negative, right? It's concave down. And at negative 8, that gives you a maximum. Does that help? Right, so we have the other critical number is 4, so plug that into the second derivative. Remember, if you plug 4 into the first derivative, you're just going to get 0. That's what makes it a critical number. So if you plug it into the second derivative, you get 6 times 4 plus 12. 24 plus 12 is 36, which is definitely positive. So a positive second derivative means concave up, 4. And if it's concave up, that tells you have a minimum. So f has a relative minimum at x equals 4, y equals, that's for you to figure out. Plug that into the original function. So again, you would get the same information if you use the first derivative test. In fact, now that we know negative 8 is a maximum, we can plug in the sign chart here for the first derivative, right? The first derivative to the left of 8, the first derivative should be positive. It's increasing. Between -8 and 4, it's going to be negative. And then when you're bigger than 4, the slope is positive, right? So again, don't get confused with the first derivative, which is the slope, and the second derivative, which is concavity, right? So yes, obviously, if you have the sign chart here, you would know immediately that at -8 you have a maximum, and at -4 you have a minimum. But the second derivative test tells you the same information, which with really not much more effort. You're just plugging in the critical numbers into the second derivative. Whereas if you use the first derivative, you actually have to plug in 3 numbers, right? You have to plug in, say, -9, something between -8 and 4, like 0, and then something bigger than 4, like 5. So you'd plug in these 3 numbers into the first derivative. That tells you that you're increasing, decreasing, and increasing, and then that would tell you whether you have a maximum or minimum at your critical point, critical numbers, sorry. But the second derivative also tells you that same information, right? And in fact, I would claim it's even easier because taking the second derivative was not much of a pain here, and then plugging in the 2 numbers was pretty easy. So that gives you the answer very quickly. Just remember, when the second derivative is negative, you might be tempted to think, well, negative means minimum, but it's actually the opposite. It's a maximum. Because the second derivative is negative means it's concave down. And if it's concave down at your critical number, that means you have a maximum. Positive second derivative means it's concave up. And concave up at your critical number means you have the lowest point, the minimum. So I hope that helps, right? Using the second derivative to determine whether you have a maximum or minimum. Obviously, we didn't run into this situation where the second derivative equals 0. If that happened, well, we would have to use the first derivative test anyways. So you're really not gaining much by using the second derivative test in that point when the second derivative actually equals 0 at the critical number. Luckily, that didn't happen here. And it usually doesn't, although there, when you go through the homework, there might be some problems where that happens. Then you just go back and use the first derivative tests, which always works, right? So the second derivative test doesn't always work. When it does work, it's typically easier than the first derivative test. Not necessarily, of course, because in some problems, finding the first derivative is hard enough. Finding the second derivative would be even harder. And I'm thinking of things like rational functions. Rational functions, you have to use the quotient rule, and you'll see that when you take the second derivative, it's unpleasant. But yeah, in most cases, in simple cases like this, taking the second derivative is not that bad. And so second derivative test is just an alternative way to find the maximum or minimum instead of using the first derivative test. So both tell you the same information. Second derivative test just gives you a different way of doing that in some cases. So I hope that helps.